Good morning, students, or good evening. Doesn't matter. So this would be a series of videos for the time wherein we cannot meet because of so many things. So in order to finish our learning outcomes and of course topics, so I'll be making videos as a support for, let's say, problem solving or probably a particular concept. So our aim is that we can really finish our um, uh, topics from the syllabus. So for of course from we're already in learning packet 2. So last time um, we discussed about Lewis dot structure or Lewis dot structure of every compound. So that was one of the LO. May I first again reiterate the learning outcomes. Of course, last week we were talking about one of our LOs is after that discussion that we had, you already have, you should already know how to uh, write the Lewis structures of particular compounds, Lewis structures. So that was the LO. So you really have to practice it for you to gain mastery of it. But of course, I'm also looking at the time. If ever there are a lot of LOs already, so I'll just be highlighting those LOs, learning outcomes, that are probably well supported. So if ever I can see it fit that those LOs are not really well supported, whether in videos or in our face-to-face discussion. So I'll just I'll just not be including that during exams and quizzes for it um, to be non-biased. So you can already write Lewis structure. Of course, you have to start with you can write the Lewis dot structures for each element. Actually, it's in the book. But anyway, as I've said, the simple rule of it is you have a periodic table, and you can see that your first group and second group will always have one electrons, and the second one would have two electrons. Again, for basic chemistry, since this is somewhat basic, but in organic chemistry is not really actually basic, but since we are finding the gap, I mean bridging the gap, so we go to basics of inorganics. So as you can see, the third group A would have three electrons, valence electrons, and so on and so forth up to the seventh. Because you can see the eighth group, which is the inert gases, doesn't really react or participate during chemistries. That's why they're not usually included with the discussion. So you only have to take note of this seven, 7 groups wherein they have valence electrons, which is also according to the numbers or the families that they have. Okay, so that's the first one, and it's so easy. You only have to look at the periodic table. After that, if you can already, or you can use actually your periodic table during making Lewis structures. So again, as a review, so if ever you will be given a compound, let's say BH3, I think BH3 is a particular compound, a stable compound. So again, you only have to look at the Lewis dot structures for it. Boron, I think, has three. Can you see it here? Boron has three. And then, so this one is simple one. Boron has three valence electrons, meaning the electrons that are only outside. And hydrogen has only one. Then since you have three atoms of hydrogen and you have only one attachment, you also have one attachment. So this is easy. All those hydrogens will attach to these three electrons from the boron. They will be sharing those three with respect to each hydrogen. So one hydrogen here, and one hydrogen here. And then the second two dots would represent a single bond. So if you convert this already to a Lewis structure, it should look like this. You have like that single bond for each shared. So again, two electrons is shared. So you can actually do it like this. It's still the same because we're just representing it in terms of a two-dimensional structure, of course. So there's nothing wrong with that. so so you can already do this. Another is maybe you have a let's say a sugar, let's say C. um, CH, amino acid, CH3. Then you have NH2, CnH2. You have H, CH3, CnH2. Then you have, let's say, COO, CO2H, CO2H. This a little bit complicated. So let's see. So you have usually what is written as a chemical formula. Um, it would be also the structure of that compound, the Lewis structure. I mean the shell, or probably how it will be look like. Meaning CH3 would be, let's say, from the other side, attaching to. You can see that carbon has four. Let's go back to basic. Hydrogen has one. So as you can see that CH3, since they are near, so you can predict that that H3 would go to the three of the electrons of the carbon. Then that one hydrogen will be particularly attached to this, because you would have a broken bond if you will put that hydrogen into this, since that hydrogen is separated from this, meaning it is not really included, meaning you can start from H and then H and then H. Then you can see what is next is carbon, so meaning the carbon has a single attachment to carbon. So this carbon is already filled because it already has 8. Those hydrogens is already filled because it already has 8. This hydrogen unfortunately will come to carbon, because since it has 1 and the carbon has 4, so there will be only 2 remaining bonds for a carbon. So the other one actually would be from nitrogen, and the other one would be from another carbon. Why? Because as you can see, your hydrogen is only one, so basically it will attach to nitrogen. Nitrogen has, I think, 5, 3, 4, 5. So two of those is already lone pairs. Generally, they can always they can actually these two might already also group up and make a um pair. But for a basic, you have three. So I think I am wrong with this. This must be three. Oh, two. Oh, so sorry. That was the right one. NH2. So for that carbon, nitrogen would of course attach. And then of course, since one ah, nitrogen is already attached, and it will also have an attachment. Yeah. So I was right, because you already have one, you still have two. You have a lone pair, and you have still two. So basically, you have hydrogen here and there. Okay. So those are the three. So you have the two, and then you would have carbon in this side. Okay, for that CO2H, and then for carbon, this one is already filled. Hydrogen is also filled. Your nitrogen is already also filled. You have a lone pair here. So take note, because we will be not notifying it. And then you have your carbon here, and it will be attached with oxygen. So you can attach oxygen here. Actually, those two oxygen, one would be a double bond. Why? Because I think that one hydrogen will just attach to the one of the oxygen, while the other one would be somewhat double bond, dead. So I think that would be double bonded, because carbon would now be nothing to attach with. So basically, this carbon should still have another one. So that should be double bonded. So that carbon would have an 8. Okay, following the octet rule. Then hydrogen would attach to it. So you can see this oxygen already has 1, 2, 3, 4, 5, 6, and then you still have a lone pair of that oxygen. And the other carbon, of course, you will attach an oxygen to it. Ooh. So this one, I think, okay. 1, 2, 3, 4, 5, 6. Hmm. So I think the other one H, so this would be a single bond. Okay, and this would be the double bond. Why? Because this hydrogen attached here. So basically, this would not be two, and I was wrong little bit earlier. I was wrong. That should not be 2. That should only contain um, of course. Okay. So it would still have another lone pair. So it has one bond, two lone pairs. Why? Because carbon, this first without hydrogen would be now the double bond. Why? Because as you can see, there's only one hydrogen. So one of them should be a double bond, and it is proper that this one would be the double bond, of course, for this carbon to be complete. So that is usually the case for CO2H. So that is a carboxylic acid, actually in organic chemistry. So that should be it. And then you again have two lone pairs for this oxygen. So basically, it's already complete as you count all the necessary necessary electrons. So if I draw that, because that was just a solution, you can have, of course, for two electrons, it should be a single bond. Then we will fill all those single bonds. Then you have hydrogen here, you have N, and then you would have of course H, and then you would have H, and you still have a lone pair for that. This one has a, let's extend it, of course. um let's extend it. It has still sorry, extend that carbon. Then that carbon would be single bonded with oxygen and double bonded with another oxygen. So by that carbon is already filled, and this oxygen would have hydrogen and still a two lone pairs, while this one also have two double bonds and two lone pairs. So that would be um the uh I think this is this is triose. Tri means it has three carbons, while it is a sugar. So this is in the family of sugar. So this would be, I think, triose. Al. So this one is an aldehyde, since they, yes, that would be an aldehyde. Aldotriose. But the proper name, of course, like that would be a general name for the naming convention or the nomenclature. But anyway, you don't have to be concerned with that, because that falls into another subject. So that is a review for Lewis structures. So again, we've already discussed this. So I just supported it with the review. Meaning you can do this. You can do this thing. Uh, you can do this thing now. If you cannot, then go to the LPs and probably on the textbooks, and you should have a practice. I think I already made a lot of examples with this. I only reviewed. Okay, I'll just cut it short, and then I will go to the next LO.